This is the third talk about basic electronics in clinical neurophysiology. The purpose of this talk is to explain the math involved in calculating purely resistor responses of resistor circuits to alternating current. As you all know, the response of real resistors to alternating current goes beyond a pure resistance response. The ever-changing nature of alternating electricity, which creates a phase shift between voltage and current, complicates the math of the real resistor exposed to alternating current. Luckily for us, during clinical neurophysiology, we are not expected to know how to do these calculations. So we will restrict our talk, as initially stated, to the math related to the calculation of the purely resistor response to alternating current on an ideal resistor circuit. This talk will be conducted in a question and answer format. The first question is: all commercial alternating current is produced by rotating a coil within a magnetic field. A, true; B, false. This is the same drawing I have so often used when talking about electrical safety and in the electricity 1 and 2 videos. I have added a little figure by the side of the turbine to represent an electrical generator, and enlarged it so you can better see what it is in this new frame. As you can see, it is the schematic representation of a generator. In this frame, I have moved the electrical generator to the side to show you how the electricity is generated when the wire rotates, propelled by the turning of the turbine blades. I have now created a diagram with a y-axis and an x-axis. The y-axis, I'm using it to indicate current or voltage, and the x-axis to indicate time. The red and green rectangles indicate the north and south poles of a magnet. The green rectangle in between the red and the green rectangles indicate the position of the part of the wire pointed by the arrow. The magenta arrow on the green rectangle indicates the position and spin of the wire. So, as the wire turns and its position changes in respect to the magnets, electricity is generated in the form of a slow changing wave. This slow changing wave is called a sine wave. This wave slowly increases in amplitude, reaches its peak, and then it starts going back towards the zero line. It progresses towards the zero line, reaches the zero line, and then goes under it. It smoothly continues in that trend till the minimum is reached, and then turns towards the zero line again and continues in that direction until the zero line is reached. In this new frame, I have introduced a totally different method of generating alternating current. That is to rotate the magnet while maintaining the wires at a fixed position. The result is the same, the generation of alternating current. In this frame, I am sure that you can recognize the symbol for resistor. I also like to introduce to you the symbol for a solenoid, which is just a continuous coil of wire. So the answer to this question is B. Next question. How many radians are in a circle? A, 2 pi, B, 1 pi, C, 3 pi, D, 5 pi. This figure, as you know, represents an electrical generator and the current it produces as the wire rotates around the magnets. When the wire of a generator turns, it makes a complete circle. We refer to such an excursion as a full cycle. That is to say, we also refer to it as a 360-degree turn or as a 2 pi radian. So the answer to this question is A. Next question. In alternating current, electrons and current are represented as traveling in the same direction. A true, B false. As you recall, when talking about direct current is depicted as traveling in a clockwise direction, whereas electrons are depicted as traveling in the opposite direction. When dealing with alternating current and electrons travel in the same direction, but they travel back and forth. So the answer to this question is A. Next question. Resistor resists the flow of electrons only in one direction. A true, B false. Resistors impede the flow of electrons in both directions. So heat is produced regardless of the direction of current when it is traveling across a resistor. I will take a second at this point to reiterate what I mentioned at the beginning of this talk. I mentioned at the beginning of this talk, when dealing with alternating current and real resistors, that unlike in the ideal resistor, which only exists in electrical circuit diagrams, the resistors in real life always have some variation in heat production efficiency depending on the frequency of the alternating current. This variation is believed to be the consequence of unintended production of electrical and magnetic fields and the reaction of the wire to them. So the answer to this question is A. Next question. The average value of a sine wave with the characteristic of alternating current is A 360, B 0, C 90, D 180. I have introduced this figure before. Here, the sine wave, as it has in the past, is being represented as arising from 0, crossing the 0 line, and reaching the 0 line again, while the slopes and maximal amplitude are the same above and below the 0 line. This configuration determines that the average of such sine wave will be 0. So the answer to this question is B. Next question. The average current over a complete cycle of alternating current is A 360, B 0, C 90, D 180. We already commented on the average value of a sine wave with the characteristics produced by alternating current as being 0. This is not only true for the value of the sine wave, but also for current. So the answer to this question is B, 0. The next question is, the average voltage over a complete cycle of alternating current is A, 360, B, 0, C, 90, D, 180. Similar explanation as we made for the value of a sine wave and we made for current can be made for voltage. Voltage behaves exactly like current. So the average voltage as expressed by this curve is 0. So the answer to this question once again is B, 0. Next question. An alternating current of 1 volt Vmax produces dash volt of direct current. A 1 volt, B 0.707 volt, C 0.36 volt, D 1.7 volt. The maximum voltage of a sine wave is determined by the voltage that separates the most from the 0 line. In this frame, you can recognize the symbol for direct current. The voltage indicates that it's been steadily produced at 120 volts. The arrow points to the finger touching a resistor, and the red color indicates the extent of the burn when the finger is kept on the resistor for a while. I have given this pain the value of 1 Ausch. In this frame, I have introduced an alternating current with a maximal voltage of 120. After keeping the finger on the resistor for the same amount of time as before, when it was exposed to direct current, the extent of the burn is less. This I have represented by 0.7 Ausch. In the lower area of the frame, I have introduced alternating current being used, but this time the voltage is being given not as a maximal voltage, but as a function of the mysterious RMS. Measuring this unit, the amount of burn that will be created by 120 volts will be the same as it would be created by direct current. And so I will give in the pain scale a value of 1 Ausch. So the answer to this question, B, 0.707 volt. Next question. The effective voltage in an alternating current circuit is given by the root mean square. A true, B false. Root mean square is an expression that was derived by empirical trial and error to be able to draw a one-to-one relation between alternating current and direct current. It was created because the average voltage or current of a sine wave with the characteristics that resulted from magnetic generated electrical activity is 0. And because the maximal voltage only occurs at 2 points in the waveform. So let us look at this frame. In it, I have introduced the concept of maximal voltage. As you can see, regardless the side of the wave is in, that is on the positive side, or in the negative side, the term Vmax is used. This is because regardless of the direction of the current, whether going away from the voltage source or towards the voltage source, power will be generated. To start understanding the definition of root mean square, it is best to start by the end, that is, looking at square. So, if we take Vmax and square it, in this case, we are giving Vmax the value of 170, we end up with 28,900 volts. Next, we will find the mean of this number. We do this by taking the number we just got from scoring Vmax, that is 28,900 volts, and dividing it by 2. So we get 14,450 volts. Finally, we find the square root of that number. So the square root of 14,450 is 120 volts. Now, if we compare the root mean square so obtained to the volt max, we find that it is about 0.7. And as you recall, 0.7 is the constant to convert volt max to volts root mean square, or making it compatible with volts from a direct current source. So the answer to this question is true. Next question. The effective amps in an alternating current circuit is given by the root mean square. A true, B false. Root mean square can also be used for current. The purpose is the same. Amp max, let's say if amp max is 30, squaring it will give us 900 amps. Then we find the mean by dividing this number by half. So we will end up with 450 amps. And then we determine the square root. The square root of 450 is 21 amps. Again, the proportion between root mean square and amp max is about 0.7. So the answer to this question is A, true. Next question. What is the current in this diagram? A, 5A, B, 20A, C, 2A, D, 5A RMS. If you recall from previous talk, I have shown you this triangle in multiple occasions. Essentially, we use this triangle to determine the missing factor once we know two other factors. This is the ohm triangle. In this case, we know that the voltage source is 10 volts RMS and that the resistance is 2 ohms. Therefore, if we divide the voltage by the resistance, we get 5 amps RMS. So the answer to this question is D, 5 amp RMS. It is very important that we do not forget the RMS added to the 5 amp. Next question. What is the power of the circuit? A, 10 watts, B, 20 watts, C, 40 watts, D, 50 watts. In this frame, I have represented the 5 version of Joule's law. We discussed this in the prior video, that is electricity part 2. In this case, because of the available factor, it is most appropriate to use the last of the triangles. The last of the triangle states that power is equal to volts to the second power divided by resistance. So, given the values that we have in this diagram, we will say that 10 to the second power should be divided by 2. 10 to the second power is 100, so that would imply that 100 should be divided by 2 in order to find the power. And once we execute this operation, we get the value of P, which is 50 watts. So the answer to this question is D, 50 watts. Next question. In alternating current, voltage and current are in phase. A, true, B, false. This diagram represents the voltage curve produced by alternating current going through a purely resistor circuit. In this new frame, I have introduced current, and as you can see, in voltage and current both go up and down at the same time, which implies that they both are in phase. So the answer to this question is A, true. In conclusion, alternating current in a pure resistor current circuit is measured by a special unit called root mean square. This unit equalizes alternating current, voltage, and current values to direct current. When such units are used, Ohm's and Joule's laws can be applied to alternating current. Thank you.